This is the Anet A830 printer, which I've assembled recently. And it is sort of something I thought, let's just have a look at the physical switches on it, so that we can relate it to the problem that we're going to be looking at next. So, this 3D printer, you'll see that over here at the nozzle, the nozzle is over here, that's the heating element. Okay, and that heating element then heats up the nozzle. Maybe you'll get a better view over here. Okay, so this is the heating element heating up the nozzle over there. There is a temperature sensor also connected to it, so we're able to identify what temperature it is. Then you will notice that there are these switches. So there's a switch over here. That is to be able to identify the motion of this head, and as it hits the switch over there, it zeroes the position of the initial position before coming across. You'll also see that there's a switch over here, around about there. Put my hand over here to the side so that you can see it being activated. So that's the other switch over there. That's for this specific bed that the 3D printing is going to be done on, to be able to move backwards. And if it hits that switch, it will also use that as an initial position, initial zeroing position or homing position, and then move from there towards this side. To know sort of whether it is reaching the end, this end over here or not. You'll notice that there aren't any limit switches over here. At the same time, just with this head, there's a limit switch over here, but there's no limit switch on this side. Okay, and then similarly, you've got a limit switch that is located over here. That's for this Z axis to go up and down, but there's nothing here at the top. And this can be problematic, because especially for this head that's going to be just moving upwards, how are you going to be able to do a calibration during a print? So in the middle of a print, if you've printed the object over here, you can't move this head downwards towards the bed because there's going to be some object that's 3D printed over here. So you might find that if it's a large print, you might actually need to do a calibration in the middle of it. So in that sense, it would be probably better to have this limit switch in terms of knowing that you've hit the bed or the table and can't go any further than that. At the same time, there might be some value to have a limit switch over here, and that will allow you to actually do a calibration during a print, or even if this axis should move all the way to the top, it would stop over there if it's a very high object that's being printed. Okay, so we are going to be taking into account that we've got, again, this heating element over here. We've got a temperature sensor connected to it as well. We've got x-axis bed, which we'll assume it's this motion over here, for this to move up and down like that, and therefore it's got two limit switches, so one at the back over there, and we're going to have another one over here in the front, so that if it hits over here, we will know it's reached the limit. And essentially, in this specific problem, we're not going to be too worried in terms of the printing ability and stuff. We're going to be more focusing on terms of having this bed move up and down at the same speed, or at a certain speed we want it to be. So it will come to this end, it will stop, the limit switch will activate it, and it will go to the opposite direction. And so that's what we're going to be looking at for this specific example. So let's look at this 3D printer example. So we had a look at the problem in an earlier video. We drew up this schematic diagram as to how we're going to connect everything to it. But now we've got to look at how we're going to go doing the code. Okay, so there's a few things we need to just keep in mind while doing this. And maybe I need to just give you also a little bit of more details of what the problem statement is for this and what the requirements are. Okay, so essentially these switches over here are the limit switches. So as I mentioned when I showed you the 3D printer, it will be essentially if one of these switches should be activated, it's going to change the direction of this motor and then go in the opposite direction until it hits the other limit switch, which then changes direction back. Okay, we've got a temperature sensor. Again, we're going to have to look at a temperature sensor's data sheet specifically to be able to know what the voltage output would be for a certain amount we want to try and have. So let's say your filament needs to be 200 degrees Celsius. Is that going to be a voltage coming out that might give you an analog to digital value of 200? It might be that it's lower analog to digital value, but for this problem we're going to assume that the reading we get on the analog to digital conversion pin over here is going to be 200 that we want to use as a threshold to correlate to the temperature we want. Okay, then this motor will be controlled using a PID controller. So this motor will allow the bed to move up and down at a constant speed. And then this heating element over here, we're essentially going to just monitor and control it. And basically every second we're going to be checking if it's maybe too hot, if it needs to cool down. If it needs to cool down, it can then do so, and then needs to then therefore switch off. So in this specific example, our heating element is it is a normal digital input output pin. It also digital output pin in this specific case. So switching on this relay only on and off. We don't want this relay to start going on and off at high speeds, and then it just creates like basically the contacts are burning out, and especially with those high currents, and could be quite annoying. So looking at monitoring it every second and switching it on and off would be a good sort of and reasonable value to look at. Okay, other than that, while we're busy looking at this diagram, let's just look again at the different pins we're going to be looking at. So over here we've got these limit switches going through this OR gate to an interrupt 0 over here, the external interrupt 0, and that's on pin 4. Pin 5 has got an external interrupt 1, which is for this optical encoder. Then if we come across over here, we've got pin 15, which is port B pin 1. And all these values in terms of what the interrupt pins are and what the port values are and stuff, I'm just correlating that with the data sheet of the microcontroller. So this is port B pin 1, and that's what we're going to be monitoring to determine which direction the encoder is turning. We've got our H bridge connected over here. So this pin 16, which is port B pin 2, we will use that to change the direction of the motor, while this pin 17 is our PWM output, specifically OC2A. Okay, port B pin 5 is pin 19 over here, which we're going to be using to control the activation of the heater. And then our analog to digital conversion pin is on pin 23 over here, which this temperature sensor is on. Also, we've got these two pins over here, pin 27, 28, that's port C4 and port C5, which we're going to be using as digital inputs over there. Okay, so we're basically going to be referring to this diagram when we set up our configurations in CVAVR, and then we'll be able to know what we're going to be using for the different scenarios. Okay, so let's go to CVAVR or Code Vision AVR, and obviously we're going to go to File, we're going to New, and to Project. Do you want to use the wizard? Yes, we do. and it's the AVR 8 chipset that we're going to be using. So our wizard is started. We've got the Atmega 328P chip over there. We've got the 60 MHz clock speed over there, so that's all good. We've got project information, so we could say this is a 3D printer problem. And okay, so that's all the information over there. Let's have a look at the first thing we need to look at. We've got pin 4 and pin 5, which are interrupt 0 and interrupt 1 that we need to take into account. So if we go over here and we look at the external interrupts, we're going to enable interrupt 0 and interrupt 1. And essentially that's going to be a rising edge we're going to detect. So if it goes from a low to a high, it will be a rising edge. And that's what we want to detect when those switches are activated. Okay, now that we've done that, let's just keep on going through over here. Well, we've got, we do have pin 15, which is port B, pin 1, which is the input. So let's go to the ports. Port B, pin 1 is the input, so that's fine over there. Port B.2, if you recall correctly, that's our output for our direction to the motor, or our direction pin. So that's port B pin 2, which is pin 16. So that needs to be an output. So we're going to change it to an output and have it as an initial value of 0. Okay. Coming back to our diagram, we can see that pin 17 over here is the PWM output for the motor. So that is OC2A. So we need to go to our timers. Go to timer 2. Okay, and we're going to be again using the system clock. Timer value, we're going to say that is 2000 kilohertz. The mode, we're going to have it as phase correct PWM top OCR2A. Okay, and this is, that's great. And then we've got our output A over here, which we're going to be using. So obviously that needs to be a non-inverted PWM. Okay. Now that we've set that, you can see I'm busy toggling between different configurations over here, and we'll save it. If I go back to port over here, you'll see that port B pin 2 still is an output set over there. If I come back to the timers over here, you'll see if I go back to timer 2, this information is still set over there. So nothing is changing as such. Okay. Then if we go back to our diagram, we go over there, you'll see pin 19, that's port B pin 5, that's an output. So I've got to go back to our port configuration. Port B pin 5 is an output and it must be a 0 initially. Okay, go back to our diagram. Let's see what it says further up over here. So pin 23 is our analog to digital conversion pin 0. Okay, so I need to go to our analog to digital converter over there. We're going to enable it. And we can go and indicate the AVCC pin or AREF pin as our reference bit over there. Oh, by the way, you can use 8 bits as an input if you wish. It depends on how accurate you want it to be. Again, I'm going to say it's free running. And essentially, yeah, so that's our settings we're going to have for that. Pin C4 and C5 are inputs as well. If you look at your diagram over here, those are inputs going to from your switches. Okay, so that's pin C4 and pin C5. So if we go to ports, port C, pin 4 is an input, and bit 5 is also input. Okay, so we've basically, with this, we've gone all around our different pins over here, and we have made sure we've got all the inputs and outputs set as we desire to be. There is one thing that we have to set, which we're not able to set in terms of a hardware configuration, and that is namely with and as what to do with the timers. And we want to essentially use timer 1 to be able to time for 100 milliseconds. Okay, so timer 1, it's going to be used. We are going to run it at, let's say, our 16 megahertz or 16,000 kilohertz. The mode we're going to have is our normal top equal to 0xFF. Okay, we're going to not activate our output A and output B over there. We're going to have a timer 1 overflow interrupted. We're going to activate over there, and we're going to keep these values equal to 0. We're not going to change them. So you'll see our initial value is 0. That is the bottom of the staircase or steps of the ladder that we are indicating over there. Okay, so at this stage we've set our timer to be able to time things. Alright, so now that we've done everything, we can go to program, we can generate, save and exit. It says port beep bit 3 is used on timer 2 OCA pin. Do you want to configure this as output? Yes, we do. And then we're going to save the 3 files with the same name. So I'm going to call it specifically over here just 3D for 3D printer.c. Project will be 3D as well. That is our Code Wizard AVR project file. Okay, so now all the code has been generated over here. Now keep in mind, we can practice using Code Vision AVR without even having any hardware connected. We can compile the code, see if it finds any errors. We can fix those errors as need be. It's not that we have to specifically have the hardware connected to program anything. So that makes it in a way nice. We are able to practice how to program these microcontrollers. Alright, so let's go down, just sort of see over here. We've got again our global variables that we have. We've got our external interrupt 0. So it's just asking us to place our code over there. We've got our external interrupt 1 service routine. So for me, generally, when it comes to having to write out your code, if it would be sort of in a typical testing environment, I wouldn't expect anybody to know what these interrupt headers are as such. You know, if you just have a comment saying the following is your external interrupt 0 service routine, and you've got your code that's between the brackets over there, I would know what it is and where you'd be placing that in your specific code. Again, the same for timer 1 and all in the interrupt 1, etc. So those are things that you know, especially if you want to maybe even write it out in a pseudocode format, it will allow you to do so. Okay, so we've got all our settings over there. We get to our main program. Our local variables have to be declared over there. There's still some settings over here. Again, these settings, if you're going to be writing out in a pseudocode or at least, you know, in some testing environment, in terms of whether you know your code or not, for me personally, I would say, well, you just have a comment saying initializing registers for this whole section, and you know, these are things that you don't need to write out any of those lines. You just need to know what is appearing over there and that these registers are being set or initialized for this specific program. Okay, so we've got all that, and then we get to our while loop 1, and we can place our code over there. Okay, so now that we've done this, let's go back to the top and let's look. Okay, so for our first external interrupt 0 service routine is over here. So we're going to have a look at the same, place your code over there. Right, so our interrupt 0 service routine, if you remember looking at the diagram over there, that is for the input of the switches. And remember, depending on the switch, if the one switch is activated, we need to change the direction of the motor until the other one is activated and change the direction of the motor. So the motor direction pin is this one over here. That's port B pin 2. Okay, so let's do that. So essentially we're going to say, well, if this interrupt is activated, so in other words, a pulse has come through this OR gate to that specific pin, we need to now check which switch has been activated. Okay, so we need an if condition over here. If pin C.5 is equal to 1. Now, see, it's already added some brackets for me over there. That's good. Alright, so if it is equal to 1, then port B pin 2 must be equal to 1. Okay, so this is going to allow the motor then to change direction, considering that its initial state of port B port B bit 2 was equal to 0. Now we can have an else statement over there, but just to make sure that for clarity purposes we can have another if statement. So if pin C.4 is equal to 1, alright, then we're going to have over here that port B.2 is equal to 0. Okay, so that's all that we need to do over here for this interrupt. All that this interrupt is going to do is it's going to check the 1 pin, see if that is a 1. If it is, it's going to change the direction of your output pin to the motor for the direction, and if it's the other one, it will change it back to 0. Alright, so now we've sorted out external interrupt 0. Now let's have a look at external interrupt 1. This is our basically what we're going to be sort of counting in terms of the optical encoder. So we're going to be looking at how many pulses. Every time a pulse is received from an optical encoder, we need to increment a variable, and but we need to check channel B to sort of see if it's a 1 or a 0 to know if it's incrementing or decrementing in value. Okay, so in this case, we're going to then say, well, again, have an if statement. If pin B.1 is equal to a 1, okay, then I'm going to have a variable that's going to be x count. So x count is just going to be a variable to keep record of how many pulses on the x-axis has been received. So x count plus plus. Alright, now obviously if port B.1 is not equal to 1 and it's equal to 0, we would then normally go and say we have an else statement of else x count minus minus. Yet this piece of code is not needed, and the reason being is that we want to connect this or be able to make sure that this motor is moving up and down at a constant speed. So we're going to assume, even if it's going in reverse direction, that it's still going. We still need to count those pulses every 100 milliseconds to keep it as a constant speed. The direction of the motor might change, but the speed of the motor is what we need to count. So this section over here, you would normally have it maybe if a motor is, if you want to be able to control a motor, and there's a possibility that there could be maybe some direction change happening, but for this specific case we're not going to need to use it. So I'm commenting this out like that. We just want to keep on counting every time we see a pulse happening. And as a matter of fact, that also means that we can take out this if statement, because whether it is a 1 or a 0, it doesn't matter. We always need to just add and increment the value of this x count. So for that, I'm just going to comment out also these curly brackets, just so that we can see that they don't interfere with us or confuse us in any way. Okay, now that we've looked at external interrupt 1 service routine, let's go down. And now we've got our timer 1 overflow interrupt service routine. Okay, so this is where we're going to have to put our code for our timer 1. So if you remember, with the calculations we performed for the timer interrupt, we identified it needed to happen 24 cycles, and then the last little bit on the final cycle. So we need to type this out. So remember, every time this interrupt happens, we said we're going to have a t++ value. Okay, so this is going to be our counter that's going to count how many times this interrupt has happened, and that's required for that overflow to happen for 20 or at least for 100 millisecond time period. So we've got our t++ over there. Okay, then if t should be equal to 24, which was what we calculated, then it needs to then go and set the values to the initial value that we've got. Okay, so that needs to make our TCNT1H value that we need to set, and we need to set our TCNT1L value that needs to be set. These registers need to be set for a value of 38,400. Now 38,400 in hexadecimal is equal to 9600. So essentially that is 96 for the high value. So we'll have a 0x96 over there, and 00 it would be for the other two bits, so that would be 0x00 over there. So those values are then set as we require to be. Now if we look at this if statement, that's also got an else condition we need to have. So then it is else if, and we've got two conditions we need to, well, essentially one condition we need to look at. So that is if t is larger than or equal to 25. Okay, so if that happens, we need to reset the clock. So that would mean that our TCNT1H must be equal to 0x00, and our TCNT1L needs to be set to 0x00. We also need to then, in a case like this, go and say t is equal to 0. Okay, and then there's a flag that I need to set. That means that we've now achieved the 4 milliseconds, and I need this flag to be set so that in the main program I can go and refer to it. Okay, so for that I'm going to have a variable of T1F, T1F, which will be our flag, so that's timer 1 flag, would be equal to 1. Okay. I'm also going to have another variable over here called temp T. So that will be our temperature time. I think, remember, I want to check it for every 1 second. So that means that I need to have this 100 milliseconds occur 10 times. And for me to then go and say, okay, well, check what the temperature is and switch on or switch off the heating element. So I'm going to increment that over there as well, and I'll be monitoring that in the main code. Now, so that's essentially what we need for our timer 1 service routine. That will then complete the code for that. Okay, so now that we've had a look at that, we can essentially come down to our main code. There's no other interrupts we need to look at. As we go past all the register initialization, we go to the while one loop, which says place your code over here. Okay, so the first thing we're going to be looking at, remember as I mentioned that we need to check if the temperature timer must be at least equal to 10 for us to then know that a second has gone past. So let's take that into account and see how that works. Okay, so if temp t is larger than or equal to 10, I am saying over here larger than. You could probably have said double equals over here. For me, the concern is what should happen in your code if, for example, this main program has not been running yet and there's been other interrupts running in the background and it's got high priorities and it's not able to get to this. Then you might find this temp t could have got to maybe number 11 or number 12. And at least that would then allow you to still then go and correct the temperature. Okay, so if that is larger than or equal to 10, then we're going to say, well, if the temperature that we're reading is larger than or equal to, well, because so the temperature, for us to read that, we need to go and actually read from the analog to digital conversion. So we can say if the read underscore ADC of analog to digital conversion pin 0 is larger than or equal to 200. Remember I said depending on the data sheet that you're looking at, but we're assuming 200 could be on our A to D converter, could possibly correlate to 200 degrees Celsius, roughly. So we're going to take that as into account, but it all depends on which temperature sensor you're using. But let's say 200 is the value we're going to be taking into account. Okay, so if that should happen, then we need our port B pin 5, which our heating element is connected to, that must be equal to 0. Okay, so we want it to switch off. If it is that it is not larger than 200 and less, that means the heating element needs to switch on. So we can have an else statement over here. And we can say that port B dot 5 is equal to 1. Okay, so that will take that into account over there. Right. Oh yes, then we've got the issue of that TIF flag, so timer 1 or timer 1 flag that we need to take into account. Okay, so as you can see, I'm using these brackets to separate my different if statements and stuff, and it places these lines around, so at least you're able to see very clearly which sections different things are. I'm not going and placing maybe code in that if condition over there and by mistake maybe, and then I don't understand why the code's not running as it's supposed to. Okay, so I'm going to have another if statement over here in our main code. And essentially it's going to be if timer 1 flag is equal to 1, then I want us to then implement the PID controller. So the first thing I need to do is, if that's equal to 1, I need to go and say T1F is equal to 0. I need to set it back to 0, so that if 100 milliseconds should occur again in our main in our timer 1 code and set it to 1, it will then allow it to alternate this value. Okay, then I need to implement the code. So what I need to take into account is our error. So our error is equal to our X reference value minus our X count. So our actual value that we are reading is going to be X count, and let's say for this specific example our optical encoder is giving out 500 pulses per revolution. Okay, so that would tell us how many revolutions we're going to have. So we need to divide by 500 over here. Okay, and what I'm probably going to do over here, because error is an integer and this can give out a floating number, I'm going to use the round statement and round it, or the floor statement. And I'm going to floor it. So basically it's going to get rid of all the, it's going to round it off and ignore all the decimal points that might happen in that calculation. Okay, so this we'll be able to know what our error is. After we've done that, we also remember for our controller, our integral controller, we need to accumulate all the errors. So we're going to have another variable that we're going to call error sum. That's equal to error sum plus our error. So we're going to keep on accumulating and adding those errors together. And keep in mind as well that this error could be a negative value as well. So it could even subtract values over there. Okay, and then once we've done that, then we can implement our code. So u is equal to u. This is now exactly the same line of text that you would have seen we've had to look in the PID controller related things. So u is equal to u plus kp multiplied by error. Okay, so I'm going to also just put that in brackets. It's always need to put things in brackets and so there's no confusion. Okay, plus ki multiplied by error sum. Okay, minus kd multiplied by kd, multiply that by previous error minus error. Okay, I mean error minus previous error. Such, and obviously because this has been multiplied by kd, we need to have these in brackets as well. Okay, so it's first going to do the calculation and then go and multiply by kd. Okay, so that is essentially our PID controller line of code. Alright, so now taking all this into account, we also need to now say, just make note what now our previous error is, so that when the next time we go and we actually look at what previous error is, so we go through running through this code again, our previous error is going to be what our current error is at the moment. So our previous error is equal to error. Okay, and once we've done that, we can then say OCR to A is equal to U. Okay, so there might be some correlation that you need to implement in terms of how the PWM value and your U value might need to be adjusted to some degree. Maybe your evolutions and your PWM value needs to have some factor multiplied to it. But for this example, we're going to assume that's not the case and we're just going to let it equal to U over there. So essentially that is the code that we're going to need to be able to program this x-axis of this specific microcontroller. So again, let's just have a look at, if we go to the top of the code over here, just see how if we've implemented everything. So over here we looked at our interrupt service routine, and essentially what we are doing is we're looking if a pin is equal to 1 or any of those limit switches are activated, and then if we would change in the motor direction, you'll see that we've come over here to keep count of the speed of motor X. So basically we're just counting the amount of pulses there might be coming from the optical encoder. Okay, we're looking at timer 1, and we're basically monitoring for 100 milliseconds. So in this case, we are checking if 24 pulses have occurred. If it is the case, we will then go and set the initial value where we've got to fly off to have our initial step that we need to go to for the final sort of cycle. We need to also have a look over here at our on our 25th cycle. We're going to reset everything to 0. T is also going to be equal to 0, so it'll be a fresh start for the 100 milliseconds. We've also got this T1F flag that's been taken into account and set to 1. And in our temp T value, we've incremented that. So that in our main code over here, we can then go and we can monitor essentially if temp T is larger than or equal to 10, so in other words, a second has gone past, we can read the analog to digital conversion, monitor if it is larger than 200, if it is, activate the heater, otherwise deactivate the heater. Or, sorry, if it is larger than 200, deactivate the heater, otherwise activate the heater. And then we're just looking at whenever 100 milliseconds have gone past, the T1 flag is activated, and then we implement our PID controller over here. Okay, now that we've done this, we've essentially done the code for this problem. The remaining task we've got to do is now compile and see if everything's working. So if you remember, you go to project, we normally go and build a code because it then generates the code that will be uploaded to the Arduino board. But now that we don't have Arduino board or any hardware connected, and just to sort of see if our code is running, we're just going to compile. So we're going to press F9. There's going to be a few errors that will be coming up. Okay, so we've got 13 errors that have come up. Let's have a look at what they are. So X count. Well, X count is used over here in our code, our main code, as well as it's also used over here in the interrupt. If you recall correctly, it's being used over there. So these need to be global variables. X count needs to be a global variable. Okay, so I need to go to declare global variables over there. So int X count is equal to 0. Why is it doing that? Okay, int X count is equal to 0. Right, now that we've had a look at that, we can then also come and have a look at the others. So it's an undefined symbol T. Okay, so that is our value of our timer that is being taken into account. And because this service routine could be exiting out of that value every now and then, we need to make T a global variable. Every time it exits a certain service routine, those variables that might be in will be reset to 0 automatically. And we need to keep count of that. So T needs to be also equal to 0. Okay, T is equal to 0. What else are we going to need? There's a few times that T is used. T1F is a flag. That's also going to be a global variable because we're using it in different service routines as well as in our main code. Okay, so T1F, which is equal to 0. We've got our temp T value, which is also an integer, which we need to also make it as a global variable because it is used in our interrupts as well as in our main code. Okay, so temp T would be equal to 0. And let's go down this error list, see if there's anything else. U, we need to take into account U, previous error, and error. We need to take those values into account as well. Okay, so U basically our U, our previous error, our error, and our KP, KI, and KD values, they are all as part of only the main program. We've also got X reference over there we need to take into account. They're only part of our main program. They're not going to monitor. You know what? Something else you could also do is, if you see with this U value, this calculation over here, would it possibly give you a floating number? I'm just thinking if that might be possible. No, it shouldn't be possible because we floored it over there, so it should be fine. Okay, so we need to declare these variables as part of our local variables. Okay, so I'm just going to make a note over here in terms of what they are. So we essentially have got error, we've got xref, we've got our error sum, we have got our KP, KI, and KD values, and we've got U. Okay, so those are the variables we need to take into account. And those variables are mainly local variables used over here for the main procedure. So we go to the main void procedure, where it starts, and here where it says declare your local variables here. Okay, so our error would be an integer, so int error, which is equal to 0. We've got our X reference, which we're going to, well, what should we make it equal to? How many revolutions does it need to do? Maybe every second, or maybe one revolution. So we'll set that equal to 1 for now. We're going to have error sum. Well, initially it's going to be equal to 0. So we're going to make that 0. It will obviously add up and increase and decrease as needed. We've got our U value, which is going to be has to be an integer because that's going to be for the PWM. So U would be equal to 0 over there. Then yeah, actually, so going back, that U value, because it's got to be an integer, we just have to be careful. Our KP, KI, and KD values could be floating numbers. Okay, so I'm going to have a float over here of KP, and I'm going to give it constant values. So it's going to be KP is equal to, we could have it as 250, KI is equal to maybe 25, and KD might be equal to 20. So these would be our initial values. We could have, well, obviously you would first set KI and KD to be 0, test to be able to find what your KP value should be. You could increase and decrease it as needed. And then as you would see with the PID tuning parameters, you would then go about to get your KI and KD values respectively. But let's say you have already done it, and you can always change it over here very easily. Okay, so just as I mentioned over here, because those can be floating values, we need to maybe just go over here and say floor of this whole floating number as such. So at least we know that this will be then eventually an integer. It will be added to the integer U, assigned to the value of U, and that would be assigned to our PWM value. Project, compile. Okay, 2 errors. It doesn't know what floor is. And that's because floor is a function as part of the math library. So over here in the beginning, I would have to include #include math.h. Okay, let's see if it compiles now. Okay, 2 errors, undefined symbol, pref error. Okay, I haven't defined what previous error is. I can assign that with the local variables for the main procedure. Okay, so come to the main procedure over here. So previous error would be equal to 0. Okay, let's compile it again. Okay, there's no errors, there's no warnings. So that means our code, there's a 95% chance that our code is, well, at least our code will run, it will compile. We'll be able to build it, we'll be able to upload the code onto the Arduino board or onto your microcontroller, and it will do something. The only errors that you're going to now experience could be maybe because of some logical errors. That would be in terms of maybe you typed a specific line of code in the wrong line, and therefore it's not doing as you would have thought it would have reacted to a certain value or to a certain input or so. So those are things that are just debugging that you've got to then sort out. But your main code is working, which is really great. One of the logical errors that you might have picked up that I haven't implemented over here, that's specifically with reference with the X count value. So if you recall, X count implements how many counts on the X axis have been detected with the optical encoder. And over here in the main code, after we've actually done a calculation of our error with the value of X count, we're actually supposed to go and say, well, X count is equal to 0. So we're resetting the value of X count, so as we get these pulses from the optical encoder, it will then count again from 0, and then allowing for every 1 millisecond time period that the PID controller can be implemented. So as you can see, essentially with CVAVR or Code Vision AVR, it's actually very easy to program any microcontroller or an Arduino board, mainly because we've got the wizard we can use, which helps us to indicate what the inputs and outputs are. It generates a code for us for the different registers, and then it allows us to, from there, just go and focus on the code that we want to implement, which is can be pretty straightforward, depending on what tasks we want to do. You can get much more advanced code, I'm not denying that, but for basic operations, speed control, inputs and outputs, it is a pretty straightforward and easy task to do. So I hope this is something that we're able to show you how to go about with using Code Vision AVR, and it will also allow you to then be able to know how to start practicing doing some code. At least you can compile it, you can test it out, and then eventually when you get to a project that you've got to do, you can then program an Arduino board by just connecting it up to the computer, program the Arduino board, and actually do some practical tests. And then eventually you would, if you want to do motor speed controls and stuff, all that you have to do is you essentially have to go up and change these KP, KI, and KD values accordingly in the beginning of your main program. So, and you can alter them. You can also change your reference value. It might be that you find that you might not want it to be 1, it might need to be a decimal value, which then means that xref would have to actually become a floating number. And then you'll be able to then also go and change those type of values and calculations. Again, that could also mean that things like your error might have to become also a floating number. But at least you know the basic concept behind this and how to implement it.